Welcome! In this unit, you will learn about exponential functions. You've already spent a great deal of time learning about nonlinear functions and linear functions, and now we will focus on a special family of nonlinear functions, the exponential functions. Exponential functions get used a lot in applications. They occur almost as often as linear functions in nature, science, and mathematics. We have already encountered examples of exponential functions in looking at population growth, radioactive decay, free fall subjects to air resistance, and effectiveness of medication in the bloodstream. So let's start with an application to see why we need an exponential function. Suppose we invest $1,000 into an account that earns 50% interest annually. The interest is more likely to be 5%, but I'm using 50% so you can see the change more quickly. The interest earned will increase the balance of our investment every year. After the first year, our initial investment of $1,000 will grow to $1,500, since 500 is 50% of 1,000. At the end of the second year, we earn another 50% on the previous year's balance. So 50% of $1,500 is $750, and now our balance is $2,250. At the end of the third year, we earn another 50% of the $2,250, which is $1,125, and that'll give us a balance of $3,375. If our money continues to increase by 50% every year, our balance will get larger and larger pretty quickly, and by the end of the 10th year, we'll have over $50,000. Suppose we track the balance of our investment over time. What if we wanted to know exactly how much our balance was after 10 years, or after 11 years? How about after 100 years, or a century? To do these sorts of calculations, we would need to have some sort of function which capture the behavior, or growth by 50% of our investment. So the function we're going to look at is something called the exponential function. Here, we have a graph, and in this graph, we see the balance for several iterations. We started with $1,000, then it increased by 50% to $1,500, and increased again by another 50% to $2,250, and again by another 50% to $3,375, and so on. What kind of function matches this behavior? If you look back at the catalog of functions you already know, quadratics, rational, linear, and you try to think about this curve over here, well, what does that look like? This curve does not look like any of the curves you're familiar with, and it's definitely not a line, so we know it's not a linear function. You might guess that the curve is a parabola because it seems to be curving up. However, that won't work for this investment problem. If we want to catch this with a curve, it would have to look something like this. We can see that this curve is getting steeper and steeper because this balance is getting large very, very quickly. And that brings us to the need for the exponential function. In this unit, we will look more closely at the structure of such functions and show where the formulas we presented in those applications originated. In the last unit, recall that a linear function, y equals y of x, with slope m, is one that has a constant rate of change, m. That is, when x is increased by 1, we get the new value of y by adding m to the old value, or the previous value of y. In contrast, an exponential function, some n equals n of t, with base a, is one that changes by constant multiples of a. That is, when t increases by 1, we get the new value of n by multiplying the current value of n by a. This gives us a general formula for exponential functions. N equals p times a to the power of t, where p is the initial value, or the y-intercept, and a is the constant multiple. A is called the growth factor if the function is increasing or growing. Now, if the function is decreasing or decaying, that constant multiple a is called the decay factor. In the previous application about the balance of an investment of $1,000 over time, the formula that models how the balance increases each year can be given by n equals 1,000 times 1.5 raised to the power of t, where n is the balance in dollars t years after the initial investment. Notice that every time t increases by 1, n increases by a constant multiple of 1.5, which we also call the growth factor. Now that we have a formula, we can begin to ask and answer questions like, what is the balance after 10 years, after 25 years? Or how many years will it take for our investment to triple? In previous units, we learned how to use the crossing graph method to solve problems like the one posed in the second question. Towards the end of this unit, you will look at the inverse relationship between exponential functions and another family of functions, the logarithmic function, to solve such questions algebraically. Although you can also solve these questions graphically as well. You actually did this in the previous unit. Remember the crossing graph method? You'll learn to solve exponential logarithmic equations, which is one of the most important skills when dealing with application problems. In addition to the problem we just looked at, where we're investing money and getting compound interest, you'll also study some other popular applications of exponentials and logarithms. There are quite a few applications, including population dynamics, which is probably the most common one you'll hear about. If we look at the population of how bacteria grow over time, you'll often see exponential growth. Radioactive decay is another popular application of exponentials and logarithms. You may have heard of carbon dating. Carbon dating is where they figure out the age of old artifacts using the decay of carbon over time. In this case, the decay is not radioactive, but we are looking at the decay of a substance. We'll also revisit some applications from earlier units, such as Newton's law of cooling, which is the law that tells us that if we put a cup of coffee on the counter, how quickly will that coffee reach room temperature? Or if you put a cold roast in the oven, how quickly will that roast reach the temperature of the oven? Newton's law of cooling is another application of exponentials and logarithms. Finally, the Richter scale for earthquakes is something you may be familiar with. The Richter scale for earthquakes is actually a logarithmic function. It's based off a base of 10. So as you can see, there are many interesting applications of exponential functions. I hope you will discover how common exponential functions occur in nature and all around us.